Very good afternoon, students. Good afternoon, Amit, Ankit, Bhagyesh, Bhumika, Chandan, Dev, Diksha, Hina, Jay, Kamalraj, Karthik, Kinjal, Priyanka, Mihir, Milan, Mishi, Mohib Hussain, Munaf, Rahul, Rinku, Sachin, Yash, Zenith. How are you all? Okay. So this is supposed to be our last lecture for the completion of the syllabus. Okay. Then we will do revision and some exam related preparation in upcoming lectures. So some doubt solving, everything we can do. Okay. So the topic that we were discussing in the last lecture, the where we left, that was related to cache coherence, right? What do we call as a cache coherence? Can you see the slides? Okay. Yeah. So you see, in a multiprocessor environment, when there is a shared memory, okay, which multiple processors can access, each processor will have its own separate cache memory also. Shared memory is, let us consider it as like a main memory. Okay. Now, the cache memory, each processor has the cache memory, and the shared memory, all the processors can access. So, it is possible that some operand or some data which is available in the main memory or the shared memory that is accessed by let us say processor 1. So when that processor accesses that data, it will definitely going to put it in its own cache memory, right? We have earlier learned how cache memory works, right? Whatever data is being utilized, that is put into the cache memory. Now there are two methods. One is the write through method, the other is the write back method, right? In the write through method, both cache and main memory are updated in the write operation, and in the write back method, only cache is updated and then it is reflected back into the main memory, right? That's the process. Now the thing is that here what happens, that processor P1 has some data. Let us say the data is X. Let me draw over here. A processor P1. Similarly, there is a processor P2. Okay, that has its own cache memory, and then there is some shared memory. Now some operand X is available in the cache memory as well as the main memory. Now suppose when processor P2 takes this operand for its some operation and then it is modifying it. Let us say it is making it X dash. So processor P2 will change the copy in its cache, right? The value X will be modified with X dash, and it will also be modified whether write through or write back method in the main memory also. But the thing is that that same operand has to also modify it into the cache memory of the other processor because it is already there, right? And that is what we call cache coherence problem. So in a shared memory where multiprocessor have the separate cache memory and each processor has its own cache memory, when one copy of the operand is changed, the other copies of the operand must be changed. So the cache coherence is the discipline that ensures that the changes in the values of shared operands which are shared between multiple cache and the shared memory, that share operands are propagated throughout the system in a timely fashion. So this is the example of cache incoherency, right? The value of X is 52 in these two different caches, whereas P1 has changed to 120, and in the main memory also X is equals to 120, right? So same variable has different values, that is incoherency. That is incoherency. Okay, now let us discuss the same thing Okay, can you see this and listen to this?
When we are having multiple processes
Students, is this video visible as well as audible?
in a single system,
Okay, good, 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 good. The volume is low. Okay, I will increase the volume. It is already maximum, dear. I will try to increase the system volume. Okay.
there is a chance for cache coherence problem because multiple processors will maintain their local cache memories of unique shared memory. So when a particular processor is using a particular copy from its local cache, it will be updating in the local cache, and there is a chance of inconsistency in the information. So there are many schemes which we call as cache coherence schemes to prevent this problem. Let us consider this example. If we say the shared memory is there and the variable x with value 24. First, CPU 1 reads the data x from shared memory. So CPU will have the x value as 24. Then processor 2 reads the data from shared memory and reads it as 24. Now CPU 1 writes this value x, means it updates the value x to 32. So if you see here, CPU 2 is not having the updated data. It will be still having 24 value, and also the shared memory will be having 24. So now at this particular point of time, if CPU 3 reads the value of x, still it reads it as 24 only, but not 32, which is updated in CPU 1. So we can see that there is inconsistency in this. Suppose if we are following right through, then we can say that the CPU 3 reads 32 because when CPU is updating the value of x to 32, it is updating the shared memory also. But still CPU 2 will be having the value of x as 24 only. So there also we are not able to completely avoid the inconsistency problem. Causes of inconsistency. Sharing of writable data, process migration, IO activity, input-output activity. Inconsistency in data sharing. Let us say that there are two processors which are using data item X from a shared memory. Then each processor local cache will have the copy of X. At this point of time, both are consistent with a shared memory copy. Now, let us assume that one of the processor modifies the value of x to x dash. At this point of time, we say that another processor and shared memory are not inconsistent with the particular processor which updated the value of x as x dash. Now, suppose if write through cache is being employed, then we say that when processor is updating the value of x to x dash, shared memory will be updated. But still, another processor will not be updating its value from x to x dash. So in the case of write back cache, both shared memory and also the another processor will be inconsistent with the processor which is modifying the value of x until otherwise the block is being replaced from the corresponding processor into the main memory. Inconsistency in data sharing. If you see here, P1 is using X, P2 is having X in its local cache, and shared memory is having X. This is before update. Let us say in the case of write through, P1 is updating the value to X dash, so obviously it will be doing in the case of main memory also or share the memory also. In the case of write back, P1 will be having X dash, P2 and shared memory both will be having the value X as it is without updating their value. So you can see there is inconsistency in the data. Then process migration. Process migration means transferring the sufficient amount of the state of the process from one processor to another processor. So here, when a particular process is being executed by one processor, after completing one particular stage, it can be moved to another processor. And from there onwards, the target processor will be executing it. Actually, the process migration will be taking place in order to share the load actually. If one of the processor is heavily loaded and another processor is lightly loaded, then the load of heavily loaded processor will be shared by the processor which is having light load or less load. So there is a chance of having inconsistency during this particular process. So if you see here, P1 is having the data value, data X in its local cache, which is same in the case of shared memory, which is before migration. Now this particular process is being migrated to P2 process, and P2 updated its value to X dash, and if it is write through catch being employed, obviously shared memory also will be updated. But if you see, it is still X only in the case of P1. So inconsistency occurs in here. Suppose if it is right back, let us say P1 updated its value to X dash, but it will not be updated in the shared memory, which is being read in the P2 while executing the process. So here, the updated value is not used by the P2 to perform the particular task. So again, here also inconsistency is occurring and the task goes wrong. Last one, inconsistency caused by IO. So here we'll take the input from the input devices to the primary memory only, but this copy will not be updated in the cache memory. So because of this, there is a chance of inconsistency of data which is in the cache memory and primary memory. Similarly, when we are sending the data to output device, it will be sending from the primary memory to the output device. Suppose if primary memory is not completely updated, then wrong data will be sent to the output device, but not the updated and correct data will be sent to the output device actually. This is nothing but inconsistency caused by IO system. There are many protocols which we refer as cache coherence protocols, which will be used to resolve all these problems. Thank you.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct, but it's wordy and hard.
In this video, we are going to see the wrong data.
Okay, so far we have seen about what is inconsistency, or what we can say cache incoherence problem, and what are the reasons of this cache incoherence problem, right? The reasons being process migration, shared operands, and the communication with the IO. Now let us see how this different cache coherency
The
problems
most
are
important point is if I
solved.
update the value, it must cause all the other copies of this location to be removed from the cache. So if all of us and bigger.
Then is this video audible, students?
Yes, sir.
Check memory systems. but it's very difficult to build. There are more. I don't know how. We're interested to hear the Intel Mike, because I'm going to update the memory value in cache. I shout out, two types of block being modified. Is this block stored in more than one cache? Because if it is, then if I update it, I have to tell somebody. And there are two types of protocol which can implement this, and I'll go through this one in some detail. Snoopy protocols or directory based. So what happens with Snoopy protocols is everybody sees everything. So it's like me, every time I update the memory value in cache, I shout out, I've updated value 53. If you've got value 53, it's up to you to make sure that you put a cross by it saying that one's out of date, okay? So in a Snoopy protocol, the idea is that you're all snooping on the bus. Basically, it's up to you to make sure every core monitors all the memory traffic. And if it's relevant to it, oh, he's updating that value, it's up to that core to update the stuff locally. So all the cores, all the processors monitor all the memory traffic all the time to try and keep everything up to date. There's no central status. All processors see every request. Now, we'll come back to directory-based later. But to see it, this is surprisingly complicated. It seems quite simple in practice. You say, like, every time anyone makes a memory request, everybody knows about it, and it's up to them to act accordingly. But what are we going to do? Well, we have to be able to invalidate cache lines. You have to be able to say, this value in the cache is no longer valid. Okay? Well, we already have a valid tag. Previously, we just used it to indicate whether data had been loaded or not. But we could just set it invalid to indicate, well, it was loaded, but now it's not relevant. But we also need an extra bit to indicate the sharing status. We need to know whether I'm the only person that has this cache line or if other people have it as well. And there's lots of implementations of this. But the main model is, as I said, all processors monitor all bus transactions. Whenever anyone makes any memory request, it's effectively broadcast to everybody. Everybody keeps an eye on what's going on. If they see an invalidation message on the bus, they have to say, somebody's saying memory location 53 is no longer valid. You have to say, do I have that? Yes, I better invalidate it. Also, if someone makes a read request and I have it, I have to give that to them. So, well, I've updated that. I better give them. They better not get it from memory because the memory's not valid. I better give them that value. It's actually quite useful to go through a very, very simple three-state example just to see how it works. So I don't know if this is possibly the simplest example you can imagine. So each cache line has three states. Okay? Each cache block line can exist in one of three states. Modified, okay? It's the only valid copy in any cache, and its value is different from that in memory. So I've read a cache line, I've modified it, but nobody else has read that cache line. Shared says it's a valid copy. In other words, it's the same as the value in memory, but other people also may have it. And invalid says it's out of date. Invalid says, well, I've got this copy in my cache, but somebody else has updated that value, and so I'm going to have to reload it. And so if we go through what happens, the processor can only do two things. It can read or write, processor read or processor write. But what I'm doing is the processor is issuing those requests to the memory system, the memory bus, and the memory bus can do three things. It can read exclusive, which means it's going to modify it, or it can flush to memory. And it's probably good if we go through a specific example. I hope I can get this right. So we've got three processors, and we've only got one piece. Simplistically, we've just got one data value. We'll call it value. The R1 means a read by processor 1. W3 means a write by processor 3. And we'll just think about one value. Okay, we're not bothering about multiple cache lines. We've got one value. And we'll read through what happens if processor 1 reads, processor 2 reads, processor 2 writes, processor 2 reads, processor 1 writes. This whole gory detail. But it's worth going through to see what happens. Now, this is a I believe, this is possibly the simplest protocol you can imagine. And even with this protocol, you can see it gets quite complicated. So, processor 1 wants to read the data. That's our first thing. So processor 1, so here's each processor, here's its value in the cache, and here's the main memory, and here's our bus. It's a cold start. The cache doesn't have it. I generate a bus read. The memory controller provides the data. The data goes into the cache in the shared state. So this is just our normal view of what would happen in a single processor example. I want to read data. It's not in cache. It's read from the memory. It's put into the cache. Shared, remember, means that 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 there may be multiple versions of this, but shared means that its value is the same as in main memory. It's just being read. Okay, that's quite simple. Processor 2 wants to read the value. Its cache doesn't have the data. It places a bus read, notify the processor and asks for data. The memory controller provides the data. Again, processor 1 will see that, but it will say, well, I don't care. He's just reading the same value as me, so I don't have to do anything. That's quite simple. That's not a problem. The first problem comes when processor 3 wants to write the value. Okay, so this is what's happening is both processor 1 and processor 2 have the value in their cache. It's the same as if actually, sorry, in this one, not obvious, but so processor 2 wants to read the value. It asks for it. It gets it from memory. It could have, in principle, got it from processor 1, from the cache. But because it's a shared state, we know that that value and that value are the same, so it gets it from the memory. It's the simplest thing to do. So the first problem comes with processor who wants to write. So it wants to write, okay? Because it wants to write, remember there's no such thing as writing when you're writing to the cache. What it's going to do is the memory controller says, well, I want to write it, and I don't have the value, so I have to read it, and it's going to do a read exclusive, means I'm going to modify it. So it does a bus read exclusive. It says, I want to read this value, and I'm going to modify it. So immediately, processor 1 and processor 3 know that processor 1 and processor 2 know that processor 3 has done a read exclusive. They immediately invalidate their values. They say, well, somebody else has grabbed this, and they're going to modify it. I better scratch off my values. They're scratched off, and then the data comes from the main memory. So now we have an invalid cache line, an invalid cache line, and a modified cache line in processor. Next, processor 2 wants to read the value, okay? It says it wants to read. Processor 3's cache is the most up-to-date value. So what happens is processor 3 actually provides the value. So this read is actually cancelled. Processor 2 issues a read, and the memory system says, okay, and you want to read, but you don't really want to read because I know processor 3 has got it. So processor 3 gives it the value. And in this simple model, it flushes it to main memory. In this model, you're never allowed to have more than one cache line with a modified value. So what it does is it flushes it to main memory to keep memory consistent. Okay? So what's happened here is, as I said, processor 2 wants to read it. Processor 3 has an updated value in its cache that's provided via the bus, but it's actually processor 2. And then processor 3 also flushes the data to main memory. Okay. And then we can go on. I think this is, again, processor 1 wants to read the data. We get the same kind of thing. We have to invalidate these values wants to write, again, the same thing happens. Processor 1 has to do a read exclusive, modify that value, and these guys have to scratch out their values, and then we can carry on. So, I mean, what these diagrams show is even in the most simple possible cache coherence protocol, you get a simple action has a lot of effects. Okay, this guy just wants to write some data, but it has a value, it goes there, and this is invalidated, and this is scratched. It all gets very complicated. And I think what you'll see is also there's an awful lot of memory traffic going on. So I won't go through all the, the final one is only that. The final one is the processor 2 wants to read the value. Its cache has an up-to-date copy. No bus transaction to take place if there's no cache. This is what we'd like to happen all the time. We'd like people to be reading data from their cache, not having all this horrible bus traffic. But you can see things get very complicated. And so the way you can represent this is you have 3 states for the cache: is modified, shared, and invalid, and various read and write
तू जब इसमें जाते सर
operations cause the cache
तो
to
आप
become
पिछले जाए के होइसी हमने कहे तरह रे
Yes, Amit. Amit, you
सॉरी
have a
सर
question?
नो सर सॉरी
to modify its state. So you have a state, you have transitions between these three states, and the transition path depend on what the action is. Now, I did see there's some textbook, I can't remember what the book is, which had the full state diagram for the Origin 2000, which was a large shared memory machine. It's actually just shared memory, but I've seen these diagrams for real machines, and they're just horrific. You know, they're pages and pages and pages of stuff in corner cases. So you can see this is obviously not a very efficient thing. You can see you could immediately improve it. Okay, you can improve it by saying you can say I have an exclusive state. This copy has not been modified, but it's the only copy in any cache. And then you know that if you want to modify it, then you're happy. You don't need to tell anybody. Oh, this copy has been modified. There are maybe other copies in a shared state. So you can in our model, if a data that had been modified, basically nobody else was even allowed to have.
See, this what it is discussing is a Snoopy method. In the Snoopy method, one operand, if it is being varied in one cache memory by one processor, that every other processor knows about this change, and so that also changes. Now, the first idea what they gave, that MSI method, where that a particular operand can have three possible state. One is that operand is modified. Second, it is a stable value, good value, and the third one, stable or shared value, and the third one is I, meaning that value in the cache is not updated, that is invalid value, right? But that results in a lot of traffic. So again, what solution was given is to use two more states, that is exclusive state and owned state. Again, this is a Snoopy method only.
Shared. So you can, these are called Mezi and Moezi. So these are the real ones. But as a mental model, if you want to have a model in your mind of how cache coherence protocols work, this simple one of MSI is a useful model to have in your mind for the kind of things that go on. Of course, in practice, it's more complicated, but this is a very useful sort of base model to have. So what are the implications for this? Well, there are a number of implications. I go back to the immediate. The first implication is that all these guys share the bus. So if you measure memory bandwidth from one processor as a gigabyte a second, if all six go, you're probably not going to get 6 gigabytes a second, because this might only be able to support 2 gigabytes a second, for example. So if you measure the memory bandwidth from a single processor or core, you get an inflated value. So it's often useful to run memory bandwidth tests with all the processors going flat. That's a fairly obvious thing that's going to happen with multiple cores. You're sharing the bandwidth. The second thing that happens is you're sharing the L3 cache. So when you do that if you do the bandwidth test with multiple cores, not only will the values be less, but the steps might be in different places, because here effectively the L3 cache will be a quarter of the size. So you might see the steps in different places, because effectively the cache sizes have changed. But the thing which really kills you can really kill you with these coherency protocols is false sharing. So it's absolutely clear that if two processes simultaneously write to the same value, you've got problems, okay? If one process writes to value A, okay, it invalidates the cache in process B. And then if process B writes to value A, it has to be read over. If you think about it, if two processes or two threads flip-flop in terms of updating a value, the entire cache line is going to be transitioning, bouncing backwards and forwards between these two threads, okay? And that's a bad thing to happen. However, if you're updating the same value from two different threads, that's your fault. Okay, you shouldn't be doing that. That's easy to see from the program, yeah? So the thread. But the problem is that the coherency is done on a cache line which is bigger than a variable. So you can get a point. You can have a situation where you have two variables A and B in your program. Thread 1 is updating A. Thread 2 is updating B. From the program, it looks like there's no problem. A and B are different variables. There can be no cache problems here. If A and B live in the same cache line, there's a problem because I update A, which also, because the updates are done on a cache line basis, invalidates the value for B. So it cannot be entirely obvious from looking at your program if two threads have cache conflicts, because it can depend on whether the variables live in the same cache line. Now, in practice, scalars and things won't live in the same cache line. The OS, the compiler will spread them out. But if you're updating different parts of an array, you can get problems. And it can be quite hard to detect. So this is the coherency is done on 64 or 128 bytes. We saw that on the Interlagos, 64 bytes. This can cause a thing called false sharing. Two processors write the different words on the same cache line. Okay, so each write will invalidate the copy of the cache, and you get lots of buffer traffic. So it can be a significant performance problem in a threaded program, and it can be quite difficult to detect. And where you see this most often is people. If people are writing a threaded program, they want to add up a big array. Okay, so they say, well, I'll get thread 1 to add up the first half of the array and thread 2 to add up the second half of the array. Fine. You declare a little array, a subsum of 2 with 2 values, and thread 1 updates the first value of the array, and thread 2 updates the second value. Okay? You've got a little array where you want to put the values from all the different threads, and you've stuck them together. So almost by definition, consecutive values in that array will live in the same cache line, and you get some false sharing problems there. And there's a small example, slightly contrived, well, contorted, but in the examples I've handed out, which effectively does that. What it does is it does simultaneous updates of 2 values, and it starts updating them this far apart, and it moves them closer and closer and closer together till they hit the same cache line, and you see the performance drop, and then you see it. So you can see how big the cache line is by looking at the performance of this loop as a function of the separation between these 2 variables. And hopefully we'll get the same answer, 64 bytes, as we did. Yeah, hopefully we'll get the same answer. And it's difficult to detect because it's not immediately obvious looking at the program source that you're doing this. First exercise is slightly off. What I want you to do is really to basically
So that was the idea regarding cache coherency. Now let me share my PPT. Okay. This we have discussed. Now what do we mean by cache coherency? Can you see the slides, students? Can you see the slides? Okay, good. That all the shared variables have the same value. Even if it is updated by one of the processor, that same value is in all the cache memory as well as the main memory. Now, what is the problem with the write back policy is that some processor is updating the value that is going to update only in the cache memory. The changes in the main memory is reflected way back after a long time, and so that remains cache incoherency. So the solution of this is Snoopy method that also we have discussed. Let us see one animation for this. Right. I'm again restarting it. There are two cache memory for processor 1, processor 2. Both are reading X value from the main memory. Value is 5. 5 is read by the both cache memory. Now processor 1 is updating the value of X to 8, and it is reflected back into the memory as well as the cache of 2. Processor 2 is changing it value 8 to 13, and that is updated in the other memory as well as cache of the processor 1. So this is the cache coherency. And we have seen how the coherency can be achieved by Snoopy method. Again, that is a lengthy method. MSI method is a way more, it is simple, but it is increasing a way more amount of traffic on the system bus. On the other hand, if we use some additional states for the operands, that would be comparatively better. Exclusive state and own state. So MOSI, MOESI, this 5 state of Snoopy method, that would be comparatively lesser traffic and simplest method for cache coherency. Is this clear, students? Okay. Now, students, you can see on the Canvas page. Right now, it is maybe under the maintenance, but I have updated one question bank, that is previous year's questions that were asked in the on the Canvas, as well as a book of Morris Mano soft copy that is also uploaded on the Canvas. I also have some various animations or the videos with me that might be helpful to you. So I will also update that for your knowledge. Okay. If you see our syllabus, unit 1, 2, 3, 4, 5, 6, and unit 10. Last problem of cache coherence and shared memory, that is also discussed. And so here we have completed our all 10 units, and in all 3 batches we have completed our 10 experiments also. Now syllabus for the mid-sem 2. Syllabus for the mid-sem 2, that will be unit 5, 6, 7, 8, 9, and 10. Unit 5, 6, 7, 8, 9, and 10. The 6 units will be there in the mid-sem 2. In mid-sem 1 we kept 4, and mid-sem 2 we kept remaining all. So now from the next lecture onwards, we will do revision, we will have doubt solving sessions. You also prepare, and in the meantime complete all the assignments. I have seen many students have submitted assignments, but there are like some students have missed the assignment submission. So now I have opened that all the links for all the assignments as well as experiments. So anyone who has not yet submitted, they can submit it again. Okay. So as well as experiments also. Now, yeah, we can have a question and answer, students, for any doubts regarding any topics of from our syllabus. Obviously, the earlier question papers that you are supposed, mostly the questions were descriptive questions. Now your questions are MCQs and objective type of questions. So prepare in that manner. What is the difference between risk and CISC? Okay. How, how much delay is there between process to be executed by RISC processor and the process to be executed by CISC processor. A CPU architecture is there, then IO designing. It is all you have to understand from the conceptual point of view and divide it and see the topics. What 1 mark question can be asked from this? Yes, Sarisa, you were asking something. Sarisa? Okay. Shall we have a revision? We still have some time, 15 minutes, students. Or if you want to ask some questions, question and answer would also be okay.
हेलो सर.
I'm open with both. Yes, Umang.
सर पीपीटी कब अपलोड कीजिएगा सर? 5 मिनट के बाद 6 से 10 तक.
Okay, yeah, sure. Actually, I was updating that only today only, but the Canvas website went under maintenance.
सर ये कंटेंट में कर दीजिएगा सर.
Let me check. I am keeping everything in one place so that there will not be a problem of multiple copies. Okay, the canvas is open right now. Earlier I had kept in the file section. Yeah, books was already given, na? Morris Mann book was already given before also. And PPTs up to 5 were there. I am uploading all the remaining PPTs right now only. Unit 6, 8. Nine, 10. And then there are some additional PPT. I am making one more folder. Those are the PPTs by Hetal madam. And that also you can refer that all 10 PPTs are there. Especially the last few topics that I had kept from her PPT. Okay. So you will have now multiple PPTs that you can refer.
सर 7 नंबर पीपीटी नहीं दिखा रहा है, अभी मैंने चेक किया हूँ.
Just a second, I'm sharing with you. You can see in the files, go to PPTs, and here you can see that unit 6.
Yes, sir. 7 is not.
Unit 6, 8, 9, and 10. Unit 7 PPT, you will get it from Hetal madam's PPT. That was discussed about, because that was all the arithmetic operations. The computer arithmetic, does it have there? Unit 7. Just a second. Yeah, unit 7, it is here. Why it is not showing here? Let me drag and drop. Okay, 7th is also available now. Then there are some videos. I'm going to put those videos also. Okay, here I had kept some videos of how 8-bit arithmetic, how CPU works. Then there is a stack pipelining multiprocessor. Now this is the recorded video. Okay, shall we have a Q&A or prepare and then ask questions? Okay, students, did you enjoy this subject? You like, or any feedback, any specific things which I can improve? Thank you, Harshil. Dhairya, expected from you. You don't like any subject. You didn't like basic electronics also. Okay, Ankit. Yes, thank you. Dhairya, particularly for you, I have paid additional attention, and still you are writing this.
Sir, sir, I don't like, but still I have studied, but it's compulsory.
Yeah, yeah. I hope it will be helpful when you go for your job.
Yes, sir. So
Expecting that you will be doing job. I don't know whether you will be entrepreneur. Especially, I know that your skills are more entrepreneurial skill. But if you are going to do job, definitely this subject is going to help you.
okay, sir, but I don't like. Truly say
Pardon?
this subject is theory based, and I don't like physical theory and some.
આપણે કેટલા પ્રેક્ટિકલ કર્યા?
સર લેબમાં તો થઈ ગયા છે આગળ, પણ હું લેબની સાથે નથી. મેં 7th સુધી કર્યા છે.
પ્રેક્ટિકલ કરો. હજુ તો જે 10th મેં જે શીખવાડ્યો છે એનો વિડીયો જોજો. હવે એવી રીતે તમે બધા જ ટોપિકના બ્લોક ડાયાગ્રામ બનાવી શકો. એક ALU સર્કિટ હોય, CPU સર્કિટ હોય. મેં તો ખાલી એક 4-bit ALU જ બતાવ્યું હતું. હવે તમારે પાઇપલાઇનિંગ કન્સેપ્ટ બનાવવું હોય તો એનો એક તમને ભણવામાં તો સર્કિટ આવી જ ગઈ છે, લોજિક ડાયાગ્રામ, તો કમ્પોનન્ટ મૂકીને કનેક્શન કરવાના છે. So at that time, see whether you are going to go for the job of web development, or suppose AI related job, or suppose software development, right? In any cases, wherever your code that you are writing, right, if you keep in mind what is the machine, how the machine is working, you will be able to write efficient code. Right? How the machine works, how your compiler works, if you keep that in mind, then if you have a processor on hand which is able to handle, let us say, 30 threads, and 30 threads each shared by three processors, where each processor is able to process 10 threads at a time, then when you are doing software development, you will be able to allocate tasks keeping in mind that the processor has the capability of dividing the task in multiple threads, so that your software's output, your response times increases. Right? What is the difference between, let us say, there is an app, that app let us consider a small game, okay, and the most famous game is Ludo, right? Now you can see that multiple Ludo games you can download from the app store, right? But some game is slow, some game even allows users from the internet, 4 or 5 users, to play the same game. So see the amount of data packets which are transferred, because multiple users are accessing the same game at the same time, very nominal data packets are required. So how it is handling, when you open an app, how much amount of time it takes for an app to open in your mobile phone? On which factors does it matter? You can see some apps opening very fast, some app you can see it is taking a lot of time. Of course there will be a vast difference about around the capability of the app, right? Like PUBG game, of course it is going to take a lot of time to load, because it has so many different functionalities. But if you compare the similar structure games, let us say Ludo and Ludo apps, those gaming apps, and still you find the difference. So where is the difference? Difference is in the programming. The programming kept in mind about the functionalities of the hardware. Now you see, all the mobile phones are not having multiple processors, right? Some mobile phone might have 2 or 3 core right now. 2, 3 is normal, right? And some mobile phone might have 4 or 5 cores. Then it is on the software development, an app, that how dynamically it can allot the tasks, how dynamically it can allot the tasks along these various processors available, whatever is available in the user's mobile phone. Right? Your software, your app is going to be independent of any user's mobile phone. Right? One person can have MI, let us say Redmi 5, and one can have Redmi 7. So it is going to have, of course, difference in the performance. But your app should be dynamic enough to efficiently utilize all the resources available in the hardware. Okay, so just some thoughts I wanted to share. And yes, from the next lecture onwards, we will have revision, doubt solving, Q&A. So please prepare everything. I have uploaded all the PPTs and videos. and complete all the submissions as soon as possible. Okay. Okay, now I request you to write your attendance in the chat box, and then we can end our today's session. Have a good day. Have a good day to all the students.
સર
Yes. Yes, Dhairya.
સર મારો કહેવાનો મીનિંગ એ હતો કે અંદરથી
No,
એમ ના
no
થાય કે
worry,
આજે
no worry.
CEO એ જ
It's all light. I know you. I personally know you. Okay, it's not. Don't worry about that part. Okay. It was just.
અંદરથી એમ ના થાય કે આજે સીઓ લઈને બેસું, એમ થાય કે જાવા લઈને બેસું, એવું બધું થાય. એમ બીજા સબ્જેક્ટ નું થાય પણ આ સબ્જેક્ટ નું ના થાય.
હા, થોડીક એક્સપેરિમેન્ટ છે ને 2-3 વાર વધારે વખત કરી નાખ એટલે મજા આવશે.
ઓકે, બીજું બીજું
એટલું કર પછી મને કે, પછી હું તને બીજા આઈડિયા આપીશ.
ઓકે સર.